In this video, we're going to talk a little bit more about how to understand statistical data. And first, we'll talk a little bit about distributions. This is referred to as distributional thinking in your textbook. And I want to remind you of something that we covered in a previous video about the nature of variables. Remember, all variables have more than one value. So, for example, height, weight, emotions like joy or anger, those are all variables. And that means we can analyze the distribution of those variables. You may recall from your K through 12 education learning things like the mean, median, and mode, as well as the range and the variance. And those are all ways in which we can quantify the central tendencies and distributions of variables. So you may recall the mean is basically the average of a group of variables. We sum them together and divide by the number. The median is the direct middle score on the range of values, and the mode is the most common score. And the full range is the greatest score that you have minus the smallest score, and the variance is calculated by taking each data point, finding out how far away it is from the mean, squaring that, and then averaging. One thing to note here is how we can show the measures of central tendency being pulled in one or another direction based on the skew of the data. So in the middle, we see a symmetrical distribution. This is where the mean, the median, and the mode are virtually identical, if not exactly identical to each other. If we have a positive skew, which you can see on the left, or a negative skew, which you can see on the right, this actually pulls the mean away from the mode, and the mean becomes a less reliable indicator of central tendency. The median is a bit better, and sometimes the mode can even be a bit better than that. In thinking about how to visually present our data, especially to a large audience, we should be careful to make sure the data are displayed in proportion to how the data were measured. For instance, take a look at the two graphs here, and just imagine they're from an experiment where people are put into one of two groups, depicted by the red and blue bars. Now, the actual data points here are exactly the same in both cases. Group A has a mean score of 7.5, and Group B has a mean of 6.5. But if you look at the graph on the left, it makes it seem as if there's a huge difference between those two groups. And if you look to the one on the right, the difference looks a lot smaller. So which is the correct way to display the data? Well, a good clue would be to look at the y-axis labels circled here in green. In the left graph, the scale is truncated, which means we can only see the data on a restricted range of values from 6 to 8. But the graph on the right, we can see the full range of possible values from 0 to 8. This means that the right graph is the best way to display the data. It's important for you to understand this distinction is not just for psychology, but so that you can be a good consumer of information from the mainstream media, which sometimes displays data in ways that are not optimal. Now, you may be wondering, how exactly do we make sense of the difference between the scores and the two groups that we saw in the last slide? One way is to do what we learned about in a previous video, which is null hypothesis significance testing. As we discussed in that other video, we say that there's a statistically significant difference between two conditions if the probability of observing these data are unlikely to happen by chance if the null hypothesis is true. But sometimes scientists end up calculating a statistically significant difference between conditions, even though the magnitude of the difference isn't very large. Remember, if a result is quote unquote significant, that just means it was unlikely to happen by chance. But that doesn't really tell us anything about how big the result actually is. This is calculated separately, and it's referred to as the effect size. Effect sizes can be small, medium, or large. Then we have something called clinical significance. This is important when we're evaluating the effectiveness of treatments for mental illnesses. So let's say I have a study where some participants get a treatment and others get a placebo, and this gives us a quote unquote statistically significant result with a moderate or medium effect size. But this still may not be clinically significant if the participants with mental illnesses are still suffering from those same symptoms as they had at the beginning of the study. In order for a treatment to be clinically significant, it has to actually help people overcome their symptoms. Now we're going to talk a little bit about the concept of generalizability, or how we can actually derive meaningful information and knowledge about populations from our samples. And I want to share with you the hourglass analogy. So at the top of the hourglass, we start with a population of interest, and that population could be all human beings throughout the world. It could be just people living in America. It could be just children or just people with mental illnesses. Anyway, we start with a population of interest, and then we collect a sample, which is almost always much, 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 much smaller. So let's say we wanted to understand the population of adults 18 years and older living in America. We might collect a sample of maybe 1,000 to 2,000 individuals, even though we're talking about a population of hundreds of millions. The ways in which we do statistics and experimentation on that specific sample, which is the skinny part of the hourglass, allows us to draw conclusions about the population at large. Now, some of you may be asking, how is this possible? How is it possible to take a sample of, let's say, 1,000 to 2,000 people and generalize to a population of hundreds of millions? Well, the first thing we need to do is to make sure that the members of the sample are similar to those in the general population. So ideally, the sample demographics will be proportionate to the population demographics. And this means proportionate in terms of things like race and gender and the specific age. If we're talking about everyone 18 plus, we want to make sure we have those who are young adults represented and those who are older adults. If we don't have exactly proportionate numbers in those buckets, we can often account for the differences by weighting. So let's say we have slightly more men than women in our sample. When it comes to analyzing the data, we can weigh the data from the women a bit more than we would weigh the data from the men. A good way to achieve generalizability in our sample is to use what's called random sampling. This means that everyone has an equal chance of being selected to be in the sample of our research study. If we use what's called random digit dialing and just dial phone numbers randomly, then in theory, everyone has an equal probability of being selected to participate in the study. And then we have what's called a margin of error. In polling data, that's usually how it's referred to. In other areas of social science, we sometimes call it a confidence interval. And this means that we would expect the mean to fall within a range of values most of the time. So for a 95% confidence interval, we would say that if we do this type of sampling method over and over again, 95% of the time, it's going to fall within a range of values that is close to the mean. Usually with population sampling, we have margins of errors that are maybe 3 points off from the mean. So the range of values might maybe plus or -3 for whatever value that is. Now, we discussed in a previous video how correlations work. And I mentioned that correlations do not allow us to establish causality. They do not allow us to conclude whether one variable actually caused a change in another variable. In order to establish causality, we need true experiments. So over the next few slides, we're going to look at an example of how we develop an experiment to answer a question of causality. So in this example, we start out with correlational data. We observe that there's an association between being religious and being more altruistic. Religiosity correlates with generosity, but we can't conclude that there's a causal mechanism here. Maybe there's a third variable in play that causes people to both be religious and also be more generous. So one solution is to design a true experiment. And in this case, we first have to divide our variables into the independent and dependent variables. The independent variable in this experiment, and by the way, this is a real experiment that some researchers did. The independent variable is religious thoughts, and we manipulate this variable with random assignments. The operationalization, or the method that was used for the independent variable, is a word scramble task. half of our participants are put into a group that gets religious themed words in the word scramble task, words like spirit and prophet and Bible that are meant to activate religious thoughts. And then the other group of participants get neutral themed words in the word scramble task. They see words like table and chair. Now, it's very important to understand that the purpose of random assignment is to ensure that there's no other differences between these two groups. If people are put into these groups randomly, that means there's no other variables that distinguish them. In other words, it's not like we put all the tall people in the religious themed group and all the shorter people in the neutral themed group. Everyone has an equal chance of being put into either group, and that's decided usually by a coin flip. Now, our dependent variable here, which in this case is altruism, is determined by the amount of money that participants choose to donate to another player in the game. And we see the result here depicted by these two graphs, that in the neutral prime group, the average dollar amount was just over $2.50. And in the God Concepts prime group, the religious themed group on the right, we see it's about $2 more than the other group. And this is a statistically significant difference. So we can say here that there's evidence that when people are having religious thoughts in their mind, they become more generous. It's very important to understand here that any statistically significant difference between the two experimental groups cannot be attributed to any other factors. The only thing that was different between those two groups was the independent variable, which we manipulated. There's no other differences between those two groups because participants were assigned to them randomly. That does allow us to conclude that there was a cause and effect relationship between these variables. Now, you might be thinking, okay, this is great. This is clearly a superior method to doing correlational research. Are there any drawbacks here? And the answer is, yeah, actually there are. I mean, in this study, the researchers didn't really manipulate whether people are religious or secular. They activated religious thoughts in one of the two groups compared to the control group by giving them some words that in theory got them thinking religious thoughts, but that could have been very temporary. And who knows if they would be thinking those things all the time if they were actually religious. Now, we do have the other correlational data that adds to this. So I think the best approach would be to say, let's look at experimental data and correlational data together to see if they give us consistent results. And then we can have a lot more confidence, not only in the cause and effect associations, but the association between the two variables in general.